Today's lesson is on finding limits algebraically of continuous functions and rational functions. So first thing we're going to look at is what is the definition of a continuous function, and we're going to we're not going to get into the explicit definition of a continuous function. We're just going to basically say that a continuous function is a function that you can draw without picking up your pencil. So for example, we might have the function f of x equals x cubed, and in that case you would draw the function without being able to pick up your pencil. That's a continuous function. So an example of a non-continuous function would be something that has a break in it, like a piecewise function might be non-continuous, or something with an asymptote might be not continuous. So when we're looking at a continuous function, you can see, I'll just draw any continuous function here. If I say what is the limit as x approaches, let's just use 2 as an example. We'll call this g of x, and let's say 2 is right there. Then the point at which that is, so the limit as we get closer to that point is going to be the exact same thing as the point itself. So in this case, the limit is going to be equal to the function value at that point, and that's going to be true anywhere on any continuous function. So those are the easiest ones to find. So just as a quick example, if I said what is the limit as x approaches 5 of 2x squared, well, we know that that's a polynomial, so we know that that is continuous. So if I want to look at a graph, I can look at a graph and say, well, 2x squared is just a parabola, and when I'm at, let's just say 5 is right there, I just need to figure out the limit is going to be the same as the function value, so I'm just going to plug in a 5 into that function. So the limit is going to be 2 times 5 squared, which is 50. And that is what we call direct substitution. So anytime we have a continuous function, or even just a piece of a function that's continuous, then we can use direct substitution. And that's what we're going to try first in almost all of our function examples, all of our limit examples, is direct substitution. We're going to try to plug in a value and see if we can get a number, and if we get a number, then we're good to go on our limit. All right, moving on, review of rational functions. So let's recall that if I have a factor in the numerator, then that means that it is an x-intercept. If I have a factor in denominator, I'm going to say only, same thing up here, only. Then I have a vertical asymptote, and if I have factor in both, that's when I have a whole. So, and then finally, that's all of our points over there. And then our last review is horizontal asymptotes. Again, just in case we need a little refresher, there are 3 cases when the degree of numerator is larger, then we do not have a horizontal asymptote. We have what's called a slant asymptote, which means it's either going up to infinity or down to negative infinity. It's not getting closer to any number. if the degrees are the same, that's when I have a horizontal asymptote of y equals 0. And the third case is when the degree of the denominator is larger. And in that case, I still have a horizontal asymptote, but I have to look at the leading coefficients of the numerator and denominator to get my horizontal asymptote. So these are going to come into play when I'm looking at limits as x approaches plus or minus infinity. And these are going to come into play as I'm looking at values like 2, -2, 7, whatever it might be. All right, so let's take a look at some examples. Example 1, it says evaluate the following limits. Limit as x approaches 2 of x cubed. So the first thing I'm going to try is direct substitution. I'm going to plug in a 2, and when I plug in a 2, I get 2 to the third power, which is 8. And that is my limit. Again, just as a drawing, x cubed looks like this. I plug in a 2. That connects over here at 8. The limit is the exact same thing as the function value, so I get 8. All right, let's try part B. Similar. I'm going to try direct substitution. I'm going to plug in a -3, 2 to the -3 squared, plus 4 times -3 plus 1. Simplify that. I get 18 minus 12 plus 1, which is 7. So the limit is 7. Go ahead and pause the video for right now and work on examples C and D. Okay, I'm assuming that you have finished examples C and D, very similar to the first two. Doing direct substitution, you can plug in a -3 for example C and get an answer of -2. Same thing with the direct substitution in part D, and you get an answer of